You're listening to DTFHN for April 25th, 2026. I'm your unsigned and unobfuscated host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who name things for a living still can't agree on what to call anything. Today's a day for appreciating craft in strange places and watching old problems finally crack. Let's get into it. USB networking has a fundamental physics problem, and this story is a beautiful illustration of what happens when you slam into it. For years, if you wanted 10 gigabit Ethernet on a laptop, you needed a Thunderbolt adapter. Big, hot, expensive. We're talking north of $200 for a brick that could warm your coffee. Now there's a new generation of adapters using the Realtek RTL8159 chipset. $80, fits in your palm, runs cool, and it plugs into a standard USB port instead of requiring Thunderbolt. There's just one problem. USB bandwidth is a mess. Jeff Geerling tested this adapter on 4 machines and only one of them. A desktop with a USB 3-point Patriot Gen 2 passport actually delivered the full 10 gigabits. The laptops? 6 to 7 gigs, tops. And here's the comedy. To even figure out whether your computer has the right kind of USB port, you'd need to be a detective. Windows reports all USB 3.x connections as just USB 3.0. Most manufacturers don't label port speeds. Apple at least shows negotiated speed in system information. Microsoft doesn't surface it anywhere obvious. Run this forward. You buy a 10 gigabit adapter. You plug it in, you get 6 gigabits. Was it the adapter, the cable, the port, the driver? On Mac, it works immediately, but the settings panel claims you're connected at 2.5 gig when you're clearly not. On Windows, it won't even connect until you hunt down a driver from Realtek's website. The hardware works. The software ecosystem around it is held together with duct tape and naming conventions designed by a committee that apparently hates clarity. The USB Implementers Forum has renamed these standards so many times that the same physical spec has had 3 different names. This isn't a technical limitation. It's an institutional failure of communication. The silicon works fine. The engineers at Realtek solved the hard problem. Then the spec naming people and the OS vendors fumbled the handoff to actual humans. Now here's what's genuinely exciting. That framework laptop in the test was a DePi just announced a framework expansion card. A 10 gig Ethernet module that slots directly into the chassis. No dongle, no adapter. Just snap it in. That's what happens when you design a laptop as an open platform. Third-party hardware makers show up and build things you never planned for. Framework didn't need to make a 10 gig card themselves. They built the socket. The ecosystem did the rest. If you already have a 10 gig network and you're using RJ45, $80 for a pocket-sized adapter is a genuine upgrade over the Thunderbolt bricks. Even at 6 or 7 gigs on most laptops. If you don't need 10 gigs, a $30 5 gig adapter gets you most of the way there. The value curve favors patience and knowing your own ports, assuming anyone can figure out what their ports actually support. The tools exist. The silicon is there. The pricing has finally come down to reasonable. Now if someone could just fix USB naming, we'd really be in business. Moving on. In Ahmedabad, some microsystems poured $3.5 billion into acquiring Star Division, mostly to get Star Office, which they then open-sourced as OpenOffice. The logic was straightforward. Spend billions to break Microsoft's monopoly on productivity software. It worked. Eventually, through LibreOffice and the document format wars that followed. But Sun didn't survive to see the payoff. The company that funded the open alternative got absorbed by Oracle, and the open ecosystem they seeded kept growing without them. Now watch Google write a check for up to $40 billion to Anthropic. Run this forward. Google already makes foundation models. They have Gemini. They have DTF. They have the infrastructure. So why pour $40 billion into a company that competes with your own products? Because this isn't an investment in Anthropic's success. It's an investment in OpenAI's failure. Amazon did the same math. Microsoft is hedging the other direction. Every major cloud provider is essentially paying insurance premiums to make sure no single company locks up the frontier. And the engineering here genuinely deserves admiration. Anthropic built something good enough that 3 separate hyperscalers are fighting to fund it. Claude isn't winning because of marketing or distribution. It's winning because the craft is visible in every interaction. The constitutional AI work, the interpretability research, the iterative deployment philosophy. This is a team that publishes its methods. You can read the papers, you can trace the reasoning. That transparency is doing real work in a market where trust is the scarcest resource. But $40 billion creates gravity. Gravity bends trajectories. The interesting question isn't whether Anthropic can build great models. They already do. The question is what happens to the architecture of control when your 3 largest investors are also your 3 largest cloud platforms, each selling your product through their marketplace, each running your models on their silicon, the open source models, Llama, Mistral, the whole flourishing ecosystem. Don't have this problem. Nobody writes a $40 billion check to a model you can download and run yourself. That's the feature. The commodification everyone keeps warning about isn't a threat to AI progress. It's the path to AI that actually serves people instead of quarterly earnings calls. The tools should be everywhere. The question is whether $40 billion helps that happen or makes it harder. Moving on. What happens when your AI agents forget everything between sessions? It's a question that sounds trivial until you watch someone spend 40 minutes re-explaining their codebase to a model that helped architect it yesterday. Every context window is a clean slate. Every conversation a first date. We built systems that can reason about protein folding and write working compilers, and they can't remember what they had for breakfast. WPHEF. Yes, named after the fictional startup from The Office. Takes a genuinely interesting swing at this. You run one command and it spins up a team of AI agents. CEO, PM, engineers, designer, all visible in a shared workspace, arguing over tasks, shipping code. But the part worth paying attention to isn't the org chart cosplay, it's the memory layer. Every agent gets a notebook, the team shares a wiki. And here's the architectural choice that matters. That wiki is just markdown files in a Git repo. Not a proprietary knowledge graph. Not a vector database you can't inspect. Markdown. Git. Files you can open in any text editor. Diff with standard tools cloned to any machine. File over app when an agent discovers something durable. A recurring pattern. A verified fact. A confirmed preference. It promotes that knowledge from notebook to wiki, where it becomes institutional memory the whole team can access. Pull this thread and you find a genuinely Karpathy-flavored insight. The best knowledge management system for AI agents turns out to be the same one that works for humans. Plain text under version control. Every change tracked. Every edit attributable. Every state recoverable. Git solved collaborative knowledge management decades ago. We just forgot because we were busy building SaaS platforms on top of it. Now, is this pre-1.0 software where main moves daily? Absolutely. Will your AI CEO make questionable prioritization decisions? Almost certainly. Though honestly, that's true of the biological version too. But the bones are right. The memory is yours. The format is universal. The version history is immutable. You can fork it, rebrand it, swap in different agent packs. The README literally links to a forking guide. One commenter raised a fair point about probabilistic systems compounding errors over long-running tasks. That's real, but the Git-backed wiki is actually a partial answer. Every state is a checkpoint. Roll back the bad reasoning, keep the good observations, let the agents try again. The tools exist, the knowledge compounds, and for once, you can actually read what your AI team thinks it knows. 4 stories in, and we're still finding ways open models surprise us. This one's almost absurd in the best way. 58 parameters. That's how many numbers define a human body in the ANI model. The shape of your rib cage, the width of your shoulders, the curve of your hips. 58 floating point values that place you somewhere in the vast space of possible human forms. And this team is predicting all 58 from 8 multiple-choice questions. No photo, no GPU-A, forward pass through a tiny MLP that finishes in milliseconds on a CPU. Let's pull this thread because the engineering here is genuinely elegant. It starts with a paper by Bartol and colleagues from 2022, who showed something counterintuitive. A simple linear regression from just height and weight predicts 15 body measurements with surprisingly low error. Many deep learning photo pipelines can't beat it. That's humbling. But it's also incomplete. Because you and I both know that 2 people at 178 centimeters and 80 kilos can look completely different. One carries it in the belly. The other carries it in the shoulders. Height and weight alone can't distinguish them. So the team asked, what's the minimum additional signal that resolves the ambiguity? They ran a beautiful analysis. Bucket people by height, weight, and body shape, then measure the remaining variation as you lock in each new feature. Build type, belly distribution, cup size, gender. With all 8 features locked, the residual waist standard deviation drops to 1.3 centimeters. That's the theoretical floor, and their MOP nearly reaches it. Height accuracy of 0.3 centimeters. Mass within 0.3 kilograms. Bust, waist. Hips within 3 to 4 centimeters, which actually beats their own photo reconstruction pipeline on circumference measurements. And here's what I find worth admiring about the craft. They use a physics-aware loss function. The network doesn't just minimize measurement error. It respects the constraint that muscle is denser than fat, so the same mass at different body compositions produces different volumes. They're encoding biomechanical reality into the training signal itself. That's not a hack. That's careful engineering. The whole thing is a questionnaire. 8 questions a user can answer in 30 seconds. No scrolling for the right photo, no lighting requirements, no privacy concerns about uploading images of your body to a server. The code runs locally. The model is small enough to ship in a browser. This is bootstrapism at the measurement layer. A digital twin of your body derived from questions you already know the answers to, running on hardware you already own. The blueprints are in the blog post. The method is reproducible. Anyone with a training set can build their own. When the most accurate path is also the most accessible one, that's not a coincidence. That's good architecture. Good architecture shows up everywhere, even in something as deceptively simple as counting frames per second. Measuring a heartbeat is one of the oldest diagnostic acts in medicine, and the method has never changed in its essence. You count pulses over a fixed interval of time. not one pulse, not the last 5 pulses, regardless of how long they took. You pick a window, usually 6 seconds, count the beats, multiply by 10. The window is constant. The measurement fits inside it. This is how you get a number you can trust. FPS counters in games are supposed to work the same way. Frames per second. It is right there in the name. Frames per second. A count of events within a fixed unit of time. And yet, the most common implementations get this wrong in ways that are genuinely instructive about how easy it is to measure the wrong thing confidently. The first mistake is measuring a single frame's duration and inverting it. One frame took 8 milliseconds. Therefore, you are running at 125 FPS. But that number is instantaneous. It flickers faster than anyone can read it. You have turned an aggregate metric into a point sample, which is like taking your pulse from a single heartbeat and declaring your resting heart rate. The second mistake is subtler and more interesting. You keep a rolling window of the last 5 or 10 frames, average their durations, and invert. This sounds reasonable until you realize the window's duration in real time depends on the thing you are measuring. When frames are slow, your window stretches across a longer period. When frames are fast, it contracts. The measurement instrument changes shape based on what it is measuring. In cardiology, this would be like saying you will count the last 5 heartbeats. During exercise, that is 2 seconds of data. At rest, it is 4. You have built a ruler that bends. The correct approach is what any scientist would do first. Fix the window. 1 second. Count every frame that falls inside it. Report that count. The window slides forward in time. Frames age out of it. New frames enter. The measurement surface is stable. This matters beyond games. Every system that reports throughput faces this same design choice. Fixed observation window or adaptive one, monitoring dashboards, network benchmarks, API rate counters. The principle is universal. When you let the measurement period depend on the measured value, you have introduced a feedback loop into your instrument. And an instrument with a feedback loop is not an instrument. It is an opinion. We talked about preserving knowledge earlier. Now, let's talk about preserving literally everything else. Story 6. Paraloid B-72. The strongest case against caring about Paraloid B-72 goes something like this. It is a niche industrial polymer. It matters to a few hundred conservators worldwide. It has no compute angle, no AI angle, no open source angle. It is, by any reasonable measure, the most esoteric thing you could spend 3 minutes talking about on a technology podcast. And that case is completely wrong, because the question nobody is asking about conservation chemistry is this. Why do we accept that the tools for preserving human civilization are proprietary formulations sold by chemical conglomerates? Paraloid B-72 is an ethyl methacrylate and methylacrylate copolymer, dissolves in acetone, does not yellow, does not become brittle, does not need plasticizers to remain stable over decades. It is functionally the invisible scaffolding holding together an enormous fraction of the world's restored ceramics, glasswork, and fossils. When you walk through a museum and see a Greek amphora reassembled from 30 shards, the thing actually holding it together is almost certainly B-72 dissolved in acetone. Applied by hand, 1 brushstroke at a time. Stephen Couve at the Corning Museum of Glass started casting entire sheets of B-72 to fill missing sections of glass objects. Transparent, reversible. You can dissolve it back out with acetone if a better technique comes along in 50 years. That reversibility is the key design principle in conservation. Never do anything permanent, because future conservators will know more than you do. B-72 respects that principle at a molecular level. One of the comments on this story is from someone who kept their own surgical bone fragments and preserved them with B-72. Another asks whether you could 3D print with it. A third just calls it a stronger, harder, less brittle, clear wood glue you can dissolve with acetone. That last description is almost offensively reductive and also completely accurate. The formula is published. The chemistry is understood. Anyone with access to the monomers can synthesize it. This is what preservation looks like when the knowledge is open. A 50-year-old polymer still outperforming newer alternatives because the community that uses it has had decades to map every edge case, every solvent ratio, every failure mode. The accumulated craft knowledge around B-72 is as important as the chemistry itself, and that knowledge lives in published conservation literature, not behind a paywall. The things we choose to preserve say something about us. The tools we use to preserve them say something too. We've gone from mass spec to polymer chemistry today. Paul, why not whales? Story 7, Humpback supergroups. 304 individual humpback whales identified in a single day, December 30th, 2025, off the west coast of South Africa. That number, as far as anyone can document, the largest count of large whales ever recorded in one observation period in human history. And the detail that stays with me is the breath. A humpback's blow exits the lungs at over 300 miles per hour and rises 23 feet into the air. 200 of them surfacing together, and the photographers describe it as looking like the Manhattan skyline. Except this skyline smells like fish and brimstone because, and I'm quoting directly, the whales burp and fart all the time on a ginormous scale. The comedy writes itself, but the history underneath it is genuinely remarkable. In Untangles or Sixtins Watabuidu, to one of be in Tarntaus and some farcum citrus, the ass points are poor as exertishers on them reduced by more than 95%. The Southern Hemisphere population, which is what we're seeing off South Africa, had dropped from an estimated pre-whaling population of over 100,000 to somewhere around 5,000. The species was functionally on the edge of collapse. What's happening now, 60 years later, is the return. These supergroups, aggregations of 100, 200, 300 whales feeding together, are behaviors that probably existed for millennia before industrial whaling erased them from living memory. We're not witnessing something new. We're witnessing something ancient reasserting itself because we finally stopped killing it. This maps onto a pattern I think about constantly. Complex systems, left alone, will self-organize in ways that surprise the people who thought they understood them. We spent decades modeling humpback behavior based on populations that were traumatized remnants. Now, the population recovers, and suddenly, there are emergent social structures nobody predicted, because nobody alive had ever seen them. The baseline was wrong because the baseline was broken. One of the comments called it the Entmoot of the sea. That's better than anything I could write. 300 ancient intelligences, gathering in numbers not seen in generations, doing something we don't fully understand yet. The ocean is running code we've never had the data set to read. And finally, the sample size is growing. 8 stories in, we're still finding bangers. This next one genuinely delighted me. Haas, mathematicians just cracked a problem that's been knotted up for decades. Every system I have ever built or analyzed has the same foundational problem buried somewhere in its architecture. Classification. You have 2 things. Are they the same thing or different things. It sounds trivial until you realize that the entire utility of your system depends on getting that answer right and getting it fast. Knot theory has been stuck on exactly this problem for over a century. Mathematicians have tools called invariants that measure properties of knots. Feed two knots through an invariant, get different outputs. You have proved the knots are distinct. Simple. Except, here is the constraint that matters. The invariants that are powerful enough to actually distinguish complex knots are computationally brutal, and the ones you can calculate quickly are too weak to tell knots apart once things get complicated. Dror Bar-Nathan at the University of Toronto put it perfectly. Say 300 crossings, and then say the word compute, and you are in science fiction. Strip away the formalism, and this is a classic engineering trade-off. Resolution versus speed. You can have a sharp lens or a fast lens. Picking both is supposed to be impossible. Bar-Nathan and Roland van der Veen just picked both. Their new invariant computes cleanly at 300 crossings. They have pushed aspects of it past 600, and it is not sacrificing discrimination to get there. The output for each knot is a hexagonal pattern, symmetric and unique, like a fingerprint rendered as a snowflake. Gil Kallai compared it to a new telescope that simultaneously sharpens resolution and extends range by a factor of 10. That is not an incremental improvement. That is a phase change in what questions you can even ask. What I find genuinely beautiful about this is the craft. The elegance of finding a path through a trade-off that everyone assumed was fundamental. The constraint was not physical. It was architectural. Someone found the right abstraction, and the wall disappeared. And this is public mathematics, published, shared, available to anyone who wants to build on it. The patterns these invariants produce are already raising new questions about knot topology that nobody could have formulated before, because nobody could see at this resolution. The tools exist now. The rest is exploration. We talked earlier about tools that endure. Nothing endures quite like plain text. And that story keeps getting better. Plain text will outlive every application you have ever used, every proprietary format, every cloud-synced workspace, every collaboration platform with a monthly fee. All of them will eventually shut down, migrate, pivot, or just vanish. And when they do, the plain text file sitting in your directory will open exactly the same way it does today. That is not nostalgia. That is engineering. A new wave of tool. Markdown, Monodraw, AsifLo are building sophisticated diagramming and wireframing interfaces that output nothing but monospaced characters. And the first principles question worth asking is, why would anyone voluntarily abandon pixels? You have infinite resolution. You have 16 million colors. You have GPU accelerated rendering pipelines that can draw anything. Why go back to drawing boxes with hyphens and pipes? Let me argue the opposite for a moment. Constraint for its own sake is just aesthetics. It is the programming equivalent of shooting on film because digital feels too easy. If the goal is communication, use the richest medium available. Nobody diagrams their system architecture in smoke signal. But here is where that argument breaks. The richest medium is not the most expressive one. It is the one with the widest reach and the longest shelf life. A UTF-8 text file can be read by every editor on every operating system on every device manufactured in the last 40 years. It lives inside your source code. It diffs cleanly. It survives version control. It costs nothing to store, nothing to render, nothing to parse. The file format is the interface, and the interface is universal. The original article makes a sharp observation. Constraint practice will matter more as capability increases. When your tools can generate anything, knowing what to leave out becomes the skill. The ASCII diagram is legible precisely because it cannot be decorative. Every character is load-bearing. And these are all free tools, open, browser-based, no accounts required. The format is the freedom. Nobody can deprecate a text file. Nobody can put your boxes behind a paywall. That is the quiet power of building on something that belongs to everyone. So text files belong to everyone. Puzz, but what about your hardware? Ever checked what's listening on your audio interface's network ports? In your 9070, the Compaq engineers reverse engineered the IBM PC BIOS. Did something that changed computing forever. They proved you could look inside a black box, understand it, and build something compatible. Legally, ethically, and in the open. That act of curiosity cracked the entire personal computer industry wide open. Almost 30 years later, someone bought a Rode audio interface, got curious, and found a G-zipped tarball. The technical details here deserve real admiration. This person set up instruments on macOS to capture disk activity during a firmware update, found the firmware blob, and discovered it was just a tar.gz archive. No encryption, no signature verification, no obfuscation. 2 partitions for failovers so a bad flash doesn't brick the device. SSH enabled by default with public key authentication. A shell script handling the update logic. The entire update protocol is an HID command. The ASCII letter M to enter update mode. Copy your tarball and its MD5 hash onto the exposed disk. Then the letter U to flash. That is the whole thing. Take the design philosophy to its logical conclusion. If your firmware is an unsigned tarball and your update protocol is 2 ASCII characters over HID, you have made a device that its owner can actually own. You could build custom DSP chains. You could patch bugs Rode hasn't gotten to yet. You could learn how embedded Linux audio routing actually works by reading the thing running on your desk. One commenter worried Rode might see this and lock it down. That fear is worth naming because it captures the absurdity of our moment. We are conditioned to expect that documenting how your own hardware works is a threat to the manufacturer. The device with the unsigned firmware and the SSH server is the one that respects you. The lockdown alternative is not more secure. It is more control. Those are different things. The tools exist, the curiosity exists, and sometimes a manufacturer, whether by intention or by accident, leaves the door unlocked. Walk through it. This has been your daily tech feed for Hacker News for April 25th, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go open something up and see how it works. We'll see you back here tomorrow.